for taking the time to come. My name is Gaurav Jain, and I did a capstone on an Amazon recommendation system. So what will my project look like? What my objective of my project is to predict recommendations for users based on their past ratings. So I'm using an Amazon item rated data set, and the method I'm using is a content-based system. It's different from collaborative filtering. Content-based is based on the content of the items and the user ratings. So the scope of my project, my data set actually has 550,000 data points. I, however, only chose to use 10,000 because of the capacity of my computer. It could just not handle all that data. And the number of users that are in this data set, so this is the number of items that have been rated, and this is the amount of users that have rated those items. So one item has multiple ratings from multiple users. Multiple user ratings. And the feature I used was categories. So each item, which is all books, has a category 1 to 25. Yeah, the reason I did this is I found that it was the most prominent category for my models. So what is a content-based recommendation system? A content-based recommendation system overview is when a person likes a set of items. From that we get an item profile list of the stuff that they like. From that we can build a user profile. So we can say that this person likes these features in the items that they have rated. And from that, we build a recommendation system using the similarities, and then we recommend it to the user. So when building a content-based recommendation system, there is a couple of matrices, things that we need in order to build it. So the first thing we need is the rating of the items. So this tells us how the user likes the items. The second thing we need is the actual features of the items. And then when we match these, get the similarity, we can recommend the item. So there's a bunch of matrices we need in order to fit the system. So the first matrix we need is item profiles. So what this matrix looks like is the number of items, which is 9,905. You might think I told you 10,000 one slide back, but there were some gaps in my data where some items weren't used. So that's why it's 9,905. So it's 9,905 by the categories. So I can say that this item has this category. So I can define that as an item profile. So now I have the user profile. Now this is very important. This tells me what categories the user likes. So it's the users by the categories, the features. So from this matrix, I can determine that a user likes category 5, likes category 3, based on his ratings. So the last matrix we need is the actual ratings of the users. So this matrix is the items, the users, and all the ratings. So basically for each item, what the user has rated for it. Now this is a very sparse matrix for sure, because not every user has rated every item. It's not very concise, but I will solve that problem. So this is kind of my workflow of building from the initialization to the predictions. So the first thing is I build those matrices, then I normalize the ratings, so to get an understanding of how the person rated. Then I get the user preferences and item features matrix. I put into my gradient descent. I put into my calculating cost of mean squared error while regularizing. Going into my SciPy optimize, coming out to my optimal matrices with the optimal features, and then using a cosine similarity to predict. So I'm going to go into this workflow in much more detail. So the first thing, nearly the first thing I do is normalize. So why is normalizing so important? So say I've rated a bunch of features, and the mean rating of all my features is 4. Now that's my scale is 1 to 5 for the ratings. So that's a very optimized rating. So if I rate anything below that, that means I really don't like it. So I take the mean, I subtract it from the rating, and I get my new rating. So basically, if my mean is 4 of all the ratings that I've done, and I rated a movie 3, that will actually be a negative rating. That means I don't like this movie because my constant rating has been 4. So a regularization, which is another important feature, this is to minimize overfitting. So when a data set has a lot of features, a lot of parameters, it becomes very noisy. Now my data set, my model does not have a lot of features, but what it does have is a lot of optimization functions, which I'll get into, which causes a lot of parameters. So this is why I'm regularizing it, and this gets added back to my cost function feature, which I'll go into. So mean squared error. Mean squared error is the distance between the estimator and the estimated. So it's the difference between this, and the less it is, the better, the more accurate your estimator is predicting. So let me get into my functions. So the first function I used was gradient descent. What gradient descent does is that it's an iterative algorithm that minimizes a convex function. So basically what it's doing is I'm trying to minimize my mean squared error to get a more accurate recommendation prediction system. So how does it do this? It basically takes this convex function and finds where the local mean, the local minimum is there, and it takes the gradient of that. It then puts it into the calculating cost function, which calculates all the mean squared errors. It takes the mean of that and puts it into my SciPy optimize function. My SciPy optimize. So let me actually start with this. A SciPy optimization function is an optimization function tool that uses a bunch of different algorithms. So these are some of the algorithms it uses. What it does is it minimizes the mean squared error by constrained minimization of a multivariate scalar function. So basically what it does in my case is that it gets the mean squared error and it tries to find a function that will reduce it. So I'll go into that more. So why did I use a SciPy optimize function? So basically I use it to minimize the mean squared error. But the function that I used was the conjugate gradient algorithm. Basically what this does is because I'm getting the mean squared error from the gradient function, I'm getting the gradient of that, I'm calculating that, I'm putting it into my SciPy optimized function. It then converts that into an ISO tour graph, and it gets the angle between that. Now I can base my recommendations basically on this, and it's very applicable to sparse systems, which mine is. Yeah, so I ran 15 iterations of that on the function evaluation and the gradient evaluation. So right now I have a system that can potentially predict the recommendations for the users. But what I do with that is I then feed that into a cosine similarity. So what a cosine similarity is that it takes a vector of a user, his preferences, and the item, and that category, and sees the distance between them. So you might think that that if they're very far apart, the angle is more, and therefore my predictions will be further apart. But that's not the case, because I'm taking the cosine of it. So it's actually the vectors that are more similar, those will get higher predictions than the ones that are far apart. So finally, I get my predictions. So what does the predictions matrix even look like? So it's basically the number of users, the number of items, and the ratings of each item compared to the user. So for item X and user X, I can see how much he would rate that item based on my predictions. So this is not coming out right, but it's basically a 3D plot of a sliver of my data. So this is the actual, and this is my predicted. And it's just a sliver. I just took of one user, and he predicted 50 items. So I'm just showing you that there is distance between my predictions and the actual data. So now I have my prediction system. How do I rate it? How do I quantify it? And how can I compare it to other recommendation systems out there? So the way I use to evaluate my system is the root mean squared error. Now I talked about mean squared error before, which is the distance between the actual and the predicted. Now the root mean squared error is the root of that, the square root of that. So it's basically showing you the same thing, except it's scaling it down to where you can analyze it to compare to your model. So like if I have a rating system of 1 to 5, if I didn't square it, it would be more than that. So it could show ratings of 7 or 8. My mean squared error could be 7 or 8, which would make no sense because that's much higher than my rating system. So my RMSE score is 1.58401. Now what does this mean? This is very like arbitrary, right? It could mean anything. But what it actually does mean, if I go back, is that the sum of all my data is the distance between this point and the actual and the predicted. The sum of all that square rooted is that score, which means that on an average, I'm 1.58 off my rating. So my system is predicting 1.58 off the rating. So is this good? Is this bad? Who can tell? So it beats a dummy regressor. What a dummy regressor is it takes one thing and it just applies it to everything. So a dummy regressor would predict everybody's rating to be 2.5 out of 5. So basically that means that everything from that regressor would be on an average 2.5 distance away from each other. So my system actually beats this, and it's better than a 50% chance dummy regressor. So I can safely say that it works to an extent. It works very well. So I kind of compared it to other systems. Other systems out there. Amazon, because I use an Amazon dataset. Netflix, because they're the market leaders. So you might think, oh, my graph is bigger, so mine must be better. But that's not the case, because your RMSE score must be the lowest. So Netflix is killing it in the market right now. Amazon is kind of getting there as well. So, but they use a much better system than mine, and I'll get to that in the next slide. So, taking this system further, what really is needed in a recommendation system to compete with some of the best recommendation systems out there is a collaborative, content-based system, which takes the aspects of collaborative filtering and content-based filtering and uses a combiner to get the best results. Another thing I really wanted to look at, but couldn't at the time, was k-means. It's where I would get a k-means cluster, get a centroid feature of that. So the k-means cluster would be the users with the similar profiles. And I get a centroid of that, and I could then compare similarity to other people with similar features, like features. Yeah, so this is a quote by Albert Einstein that kind of got me going. I had gotten stuck a couple of times in this capstone, but I persevered and made my predictions. And yeah, so it's not that I was so smart, it's just I stayed with the problem longer. Yeah. Thank you. And, yeah.